Hello everyone. It's been a fruitful session on our calculus series for Unit 1. Today we are looking at Unit 2 with the same calculus, which is on differentiation. Again, I'm your tutor, Redal AC Igan with the Maths Department here in KNUST. What are we going to take through for differentiation? On slide 1, we have the sub-outlines from limits through to some applications of derivative. And I'm happy to have a mini project with my students on that. So let's look forward for that. Okay. In this lecture video, I'm going to take that of the first sub-outline, that is the limit of definition for derivative. As we discussed, the limits can be used to define continuity and derivatives, and so we are taking that of the derivatives for that. Before that, let's look at the physical intuition of derivative or differentiation. If you look at the image I have here, we've all been, if you're above 18, you've ever been a kid like what you see in the image. We can determine how a baby grew or how we humans grow with respect to our length. And then a school of thought has it that after 18 years, you don't grow in terms of the height, but you gain some weight. And so if you want to look at the change in respect, a baby grows with respect to its length, and you're looking at something like a change. So that's the first thing that comes to mind. Look at the second image. If I have a hill to climb as a driver, the rate of my speed with respect to the distance I cover will be different from when I'm declining that same road. And so in all these three images, what we can tell about here is a rate of change. The rate of change is also referred to as derivatives. Derivative is also referred to as the differentiation we want to look at. So that is basically it. Differentiation has to do with rate of change, as simple as that, of any quantity with respect to other variables. So let me write it here for you. And so differentiation has to do with the change in quantities with respect to some variables involved in the quantity. That is all. So that is the focus, rate of change. Rate of change. And so I'm going to take that of the limit aspect of it. Before that, let's look at some notations of derivatives. In notations, we are looking at the Roman numerals. Let me change the pen to a blue should do. If I want to find the first order derivative, that's differentiating the change just once, I can have it as, assuming the function is a function of f of x, I can have it as f prime of x, which is the same as d dx, because the variable with respect to our change is x, okay? The second order Roman numeral prime is like writing I above, which is the same as now differentiating this guy here for the second time. And so realize that this becomes d square f of x over, if I multiply these two guys, I'm going to get the x squared. That is how come we have that representation. And so the third order Roman numeral becomes prime of x, which is the same as differentiating the second order to get a third. Again, if I multiply this, I'm going to get the square of f. If I multiply this guys by indices, I have the x cubed. That is how we write the notation. So the fourth order is IV, Roman numeral IV. This is differentiating the third order. This we know is going to be d fourth of f, dx of 4. So I've shown you how to derive the index of the d's. It's not just the f cube over the s cube. This is wrong. No, the cube should be here. So I've shown you from this aspect, and that's how that is derived. So the fifth order, you can easily tell that it is the v, the Roman numeral, and this is going to be the f over the x to the power 5. And we can continue to the nth order, as you see here. In the nth order, we can write just f of n. If I write f of n, it's as if I'm having the index. So normally we have it in a bracket to show any good mathematician that is a derivative. So if I write f squared, it is not the same as writing f prime. F prime is the same as writing to the power 2 this way. These are correct, but this and this are not correct. So if you are using the Roman numerals, you are good to go. If not, you are using numbers, it's into bracket. And what would this give us? Is it going to be n? No. You realize that this would be the derivative of n minus 1 and then n minus 1. Look at the pattern. The fourth order, we're differentiating the cube. The third order, we're differentiating the square. The second order, we're differentiating the 1. So it means it's n minus 1. And by indices, I'm going to have the n over the x and f of x. How do I prove that? If this is the 1, the n minus 1. I have to add them. Alright, and that is what I have here. So that's the notation for u. Either you use the Newton's notation or the Leibniz notation, and that is what I just took you through on slide 3. Now to the main deal of the day. The limit definition of derivative. How do we find the rate of change using limit? If I want to find the rate of change, I know you know this is the same as f prime of x. The limit form is given as limit as h approaches some 0, f of x plus h minus f of x over h, where h is given as a small change in x. So it means that I can rewrite this as f of x plus small change in x minus f of x all over small change in x. This is the same as that. But to just reduce writing, I'm going to use the h. Okay, the limits. We've done limits using analytical and then the numerical. So any of them should do for you. Let's quickly take 3 examples and we are done. So example 1. Example 1. We want to find a small change respect to f of x is given as x squared. What is f prime of x? So this is the first now do. If I'm given f of x, then f of x plus h. Wherever I see x, what did I do? I add h to h. So this is it. No, this is not the same as saying x squared plus h. No. It is a function on its own. So it means you must add h to wherever you see x. So let's do a substitution. It means that it becomes x plus h all square because of the square minus x squared over h. If you want to simplify this, you know it's going to be s squared minus 2xh. Let's see what we have here. Plus h squared minus s squared all over h. If I want to simplify it, I'm going to get limit as h approaches infinity of, is there any cancellations? Yes, s squared cancels out, and I have h squared minus 2xh all over h. Now what's the limit as h approaches 0? Someone may not be sure, so what you can do is to simplify this. So I have limit as h approaches 0. H squared on h gives me h, minus 2x on h gives me 2x. I hope you can relate this. I'm dividing through by the h on its own. And so as it approaches 0, we're going to get negative 2x, which I doubt. It's supposed to be plus 2x. I think I've found my mistake. It's plus here. And so f prime is 2x, and that is how we use the limit. Now example 2. You are given f of x equal to x squared, and then find f prime. And the first thing I'll do is to find f of x plus h. It means wherever I see x, I place h in there. Plus 2x plus h plus 3. And using the formula, there's going to be limit as h approaches infinity of, let's help me expand this. This is going to be s squared plus 2hx plus h squared plus 2x plus 2h plus 3 all over h. I've done the expansion. No, I think I've done something wrong. There should be a minus. So let me just bring it down. So this is the same as limit as h approaches infinity. S squared plus 2xh plus h squared plus 2x plus 2h plus 3 minus the f of x part, which is x squared plus 2x plus 3, now all over the h. Yeah, so you wanted to be careful and then know what to do. I know this x squared cancel that. Don't forget, let's minus the whole thing. Let me bring a bracket here. So, yeah, and then 2x here will also cancel that. 3 here will cancel that 3. So it means you're left with just 2sh plus h squared plus 2h all over h. You must take your time and do the expansion for me. And so we have limit as h approaches 0. If I divide through by the h, I'm going to get 2x plus h plus 2. And then limit as h approaches 0. Because it's a polynomial, I can do a direct substitution. And that's going to give me 2x plus 2. And so the first derivative here is equal to 2x plus 2. Let's check if that's what we have for our answer. Yes, and that is correct. And this, I can find the second derivative. It means I'm differentiating this again, but I wouldn't get there. I just want to use the limit for now. If I want to do that, it means my f prime of x plus h minus the f prime of x all over h as the limit. So I want to clean this part. F prime prime of x equal to the limit as h approaches in 0 of that. And so this is the same as equal to limit as h approaches 0. Wherever I see x, I put h. That's 2 into bracket x plus h plus 2 minus 2x plus 2. And so this is equal to the limit as h approaches infinity. If I expand, I have 2x plus 2h plus 2 minus 2x minus 4 all over h. And so there's some cancellation going to happen. Limit as h approaches 0. This cancels that. I think that's, we'll have 2h minus 2 all over h. If I'm going to divide through by the h, I'm going to get limit as h approaches infinity of just 2. Oh no. 2 minus 2 on h, yeah. And the limit as h approaches 0 gives me 2, as expected, because the first derivative was 2x plus 2, which is 2. And so I can go on and find the third derivative, fourth and fifth and sixth. Now the last example is a trial question for you. Find derivative from the first principle. So the first principle is the use of the limit. I'm going to help you out with the h of x, which is simpler. So what's the first derivative we want to do here? Using the first principle, that's the limit. So my first thing, if I'm given h of x to be 4x cubed, it means the addition here becomes 4 into bracket x plus h to the power cube. You should know how to expand that. So by substitution, I have 4x plus h all cubed minus 4x cubed all over h. And then you have to expand and do something. At the end of the day, I expect you to get 12x to the power square. That's what I expect of you. And then with the first example, with the g of x, the first derivative, I expect you to get 2. So try it out and then let's verify the answers together. Using the first principle, please. We are using the first principle, that's the rule of the limit. And the formula is that the first derivative of a given function is the limit as h approaches 0. Is the limit as h approaches 0 of f of x plus h minus f of x all over h, where h is given as a small change in my quantity x. If I want to find the second derivative, I go to the same approach, just as I did in the second example. And so on this note, this is the use of the first principle in final derivative. In our next session, we're going to take that of the rules of differentiation. Thank you.